Okay, so going through some of the responses, let's see. Okay. Yeah, if we have time at the end, I can like talk a little bit about like everything that's going on, but otherwise, okay, so looking through things, it seems like memory and floating point are the two biggest points of grievance for most people, which is pretty normal. So we'll skip the first-ish part. I will go actually, I wrote a set up of beautiful notes for like the previous one, and I'm worried that I won't be able to live up to that one for this one. So I'll send you guys both copies in case that this like second one is missing some stuff, or if the first one's like missing some stuff. Okay, so I'll just go very briefly some important parts of memory. So like I'll like, so if you let me know if like any of this stuff is like totally like review and you guys don't want to go over it, but okay. So the idea for memory is that we have a memory frame, and then so you'll, under this assumption so far, like we're just gonna say every process has basically access to all of memory at all times for any purpose. So, and the assumption behind that is basically because nothing else needs it, we're all good. So a couple of things about memory itself. So it can be separated into a couple of sections. So sections being, the first is you can like, we're just gonna say like this is how it's gonna be divided. This is typically how it might look. It might differ depending on how many like things that are going to be like, whatever is like booted into the code part versus like each portion, it might change. And this dotted line in the middle is basically saying this is an approximation. So the very first part of memory, the lowest part, is going to be the code portion, and you can also see this being referenced as text a lot of the time. Which is what you'll see in RISC-V. Like in the header, you'll not see .code, but you'll see like .text. So it's referring to the same thing. So this is sitting in the very lowest basic parts of memory. There's some stuff that's underneath here, but we're just gonna make the assumption that code memory starts at 0. So the very lowest part, this is basically, it's not actually the C code that you're writing. What happens, you'll learn this later during the call section of lectures, so this should be a couple lectures from now. But you'll see basically, essentially what gets pushed into the code section isn't like your raw C code. It's been translated to assembly, which you guys have a little exposure to now, which is RISC-V in this class. Some other common ones like are the x86 ones, which is basically what every laptop out there ever runs, except Mac is being special now and decided not to use it. So that it gets translated to assembly language, and the assembly gets translated to machine code, which is all ones and zeros. And that's what actually gets booted out into the code portions. So that's why you might see, like, for example, if you forget to like run GCC such that like an executable gets created and you only create like an .o file or something like that, and then you try to run it, actually won't run because it hasn't necessarily been transported into memory yet. So there's nothing to run. So I'm just gonna say not your C or assembly code. So by the way, I kind of shut my finger in a door earlier this week. Let me know if you can't read my handwriting or you want me to re-explain anything. Okay, so that's what goes in the code text portion of things. So the second part of memory is going to be the static part of memory, and not static part of memory. And you might also see this being referenced as data part. You also occasionally might see this referenced as global, though that's really, really rare. The global is actually something that you might see popping up in RISC-V a little, as well as the data parts. So just know that they're all interchangeable. So what goes in here typically is, I'll use lovely green for that. What goes in here is basically things that are unchangeable. So for example, the most common things that you might see are global variables, global constants, as well as string literals. So what this means is, what are string literals? So there are 4 exact ways to create a string in C, and all of them have slightly different properties. The biggest thing that you want to know is essentially a string literal is something that's enclosed within two quotation marks. So anything that's like that is going to be considered a string literal. However, there are 2 kind of subcategories to that. The first one being the string literals that are stored in static memory. So the way that those are declared, we're just going to take a quick side tour of this. But the way that those are done is you want to have a character pointer, and it's pointing to something that has a string literal. So this portion itself is the string literal. And so what this means is just basically it's a null terminated by default. So if you write anything with the quotation marks, it automatically has the null terminator. So what a null terminator is, terminator, is it's the slash backslash and then 0. So this is considered one character. So it's in a single bracket or a single quotations. And what this is telling the system is basically this is the end of a string. So this is super important whenever you're doing any string operations, such as like string length, string copy, string compare, all of those different string.h functions. And this is really also important because oftentimes like what will happen is if you declare a string a different way, what's going to happen is if you don't have the null terminator, then it's going to go basically crash and burn because the string operators won't necessarily know where to stop. So it's just going to keep on going until either you hit inaccessible memory or you run out of memory. So that's one of the biggest things about that. There are actually, so this is the first way to declare strings. There are actually 3 other ways, which we'll hit on each individually because they're all kind of different. The second thing like that's sort of important about it is like strings can also be declared as an array. So, or declared as another pointer, sorry. So we see that there's a pointer here, but there's also another way in which you can declare it, which is the heap version. So something that you might see often is that like people will malloc, calloc, or realloc without like casting it implicit or casting it to a the actual pointer type. So you'll actually see this in this worksheet, and I'm kind of bugged out about it because it shouldn't be the case. Implicit casting is very bad. It's sometimes used in industry, but like that's beyond the scope of this class, and you don't want to worry about it. So what's going to happen is you'll want to cast it to a character pointer, and then you can do your malloc, which will include a size of in there. So, and then size of whatever you're trying to malloc space for times number of items that you're trying to do. So if you want, for example, a 6-character array, or 6 characters like, I don't know, like apple with, or no, apples. We're gonna use apples. What you need to do is essentially you have 6 characters that you're trying to represent, so you have to malloc space for 7. The reason is because you have to actually manually add the null terminator at the end. So that's something important to know. I guess moving on to malloc then, where malloc is going to be stored is classic, like it's going to be in the heaps part of memory. I'll go back to like all of this, I'll zoom out, and I'll also send you guys these notes afterwards, so don't worry about like copying down everything I'm writing. Okay, so all dynamically allocated memory, as we know, sits in the heap. So dynamically allocated memory. This includes just malloc, calloc, and realloc. So quickly going over what each of these are, malloc essentially all it does is it basically asks our revolving cycle of memory that we have access to. Is like, okay, can I get a continuous block of this size? If the belt says yes, I have this much of contiguous memory, then it's going to return that memory pointer, so where it first is in the heap to you. Otherwise, it's going to return null. So every time that you dynamically allocate something, you'll always have to check that you actually have something like, you actually have that memory. Otherwise, what will happen on is when you use it under assumption that it's memory, when it's actually in actuality null, then you're going to cause a whole bunch of memory issues. So always remember, after you malloc anything or any of the 3, always check for nullness. So okay, there's that. Now the last part of memory is going to be the stack memory, and that's the part that sometimes gets wonky because it's really easy to mistake like what goes in it. So we'll cover that in a really, really quick second. Something that I want to clarify about is you'll be able to create local strings, so stack strings basically by declaring it as an array. So as an array, you can declare it in 2 ways. You can declare it like this, in which case you just basically are telling the stack, being like, I want 30 characters worth of stuff. So you can also like whatever type that you have, like say if we do it like this is not asking for 30 bytes. It's asking for, can I have space? Can I have space for 30 ints? So the stuff inside here is how many things that you want, not the number of bytes. So what this is like, okay, I'm now asking for permission to write or read or do whatever I want with those 30 items. the stuff in there currently isn't empty and we have access to it. It's just going to probably be garbage. So you want to know that this is technically initialized in the sense that you can start accessing things. You just can't like access necessarily what you want it to be. So this is definitively stored on the stack because it's local. Another way in which that you can declare a local string is actually kind of special. So we're going to have like an empty array size, and what's going to happen on the right hand side is we're going to have a string literal over here. So then again begs the question, why is this section not in static memory? The reason for that is because the compiler during compile time, what it'll be like is saying, okay, the right hand side, cool, that's static memory. And then it looks at the left hand side, it's like, okay, wait, I want an actual array. So it's going to basically turn whatever bytes or like whatever characters that you have on the right hand side, including the null terminator, and be like, I'm shoving it into an array of appropriate size. So this is super useful if you know exactly what you want space for. So like if you want to have like, I don't know, some amount of strings that you already know beforehand, then this is probably the way to go because it's least prone to mistakes because you don't have to account for the null terminator and you can edit it at the end. The only thing about this is because it's declared on the stack and it's sitting in memory on the stack, as we'll see later, we won't actually be able to return this. Okay. So that was a lot of talking. Something else that I really want to cover real quick before we move on to the question is what actually goes in the stack. So will I have space here? Maybe I will. I'm just going to draw this here, and if we don't have space, we'll move it later. So the stack is too thick. The stack itself actually is consisted of stack frames. So what that means is it's so like we're going to say that there's stuff up here and stuff below here. So stuff below here, I'm going to make bright blue because we don't have access to that. And so we don't want to, basically we try to access stuff underneath that. It's going to be invalid and it's going to segfault. So our first assumption is, okay, the stack pointer, so I'm going to represent it as stack P, is sitting here. So this is the end of stack frame for function A that we have. So maybe like we called it at some point, A hasn't returned, and in turn, A calls function B. So this is function B. So when we call function B, the stack automatically grows downwards and it says, okay, I now have space for more stuff. So this in and of itself is a stack frame. So in this case, this is a stack frame. So what a stack frame consists of is it first includes the return address. So as you probably saw in the RISC-V lecture, you guys were able to kind of determine what the return address was. And essentially it's PC+4, which just means that it was where my previous instruction was before I called this function, or like when I called this function +4. And the reason is because, it's +4 is because, sorry, I'm blanking for a second, is because we're working in 32-bit memory space, which means that every instruction that we have is going to be 32 bits. Every time we jump instructions, it's going to be plus 32 bits times however many lines that we actually jumped. And so this is lines as in the assembly version, not lines as in like C code. So important distinction to make. So that's not important for this part though. So we have our return address, and then we also have our arguments. Arguments are going to be on the stack. So this means that like whenever I call, like for example, foobar, like XYZ are going to be pushed in reverse order onto the stack. So it's going to be Z first, and then Y, and then X. So that's essentially how that part works. And then after that, any local arguments, args and constants, not local arguments, sorry, what am I saying? Any local variables and constants, then it's going to be declared after that. So this is really important to know because it's a distinction of why we can't return from the stack, whereas we can return things in the heap. The reason is because when a variable is declared, it's pointing, so like if it's allocated to something on the heap, so for example, if we had this stuff, the stuff that the pointer is pointing to is on the heap. The pointer itself stores a memory address that's pointing to stuff on the heap. The pointer itself is sitting on the stack because it's a local variable, but as long as we return it, it's going to be assigned to something in the previous function call because, like, as we'll see, it's like character pointer is equal to, and then maybe we'll have like a function call. And so whatever that function returns, it's going to get stored in that, so we still have access to it. Whereas if we return something from the stack, what happens is, if we try to like say, I don't know, let's say some variable is declared here, and then we return, okay, instead of like, let's say, let's make it bright pink. Make it pink, okay. So say if we had like, I don't know, let's say like a character, let's say a character array, and it's going to be like size 30, like we said earlier, and it's blah, 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 it has stuff there. And then we're like, okay, later on we're going to do, because we know we shouldn't be returning the character array itself, because otherwise we're copying memory. So we want to return like the address to this or the reference to this. So we're going to call return, and we call ampersand array. What happens to this is the character array itself is on the stack. We know that much. So we know that the variable itself is on the stack. But we also know that because it was declared on the stack, the memory address, so ampersand array, is going to be somewhere, it's going to be like, let's say, I don't know, this hex EF370220. Let's say that that's that. This is just some random thing I pulled out of nowhere. But this memory address is going to be the blue thing. So like the blue, oh, I shouldn't have used blue. I just realized. It's fine. It's fine. Everything's fine. Well, let's make it tealish. But these two are basically corresponding to each other. And because we know that the memory address for that is on the stack, what happens is, okay, so when this function gets called, the stack pointer, oops, bad. The stack pointer then moves to here. Let's make that a little brighter so we can actually see it. Nope, bad choice color. Let's see. Let's do purple. So the stack pointer moves down. So we have access to all that memory above that. So you can use any of that stuff above. What happens though is as soon as this return gets called, what happens to the stack pointer is like, okay, now I'm gonna one by one, I'm gonna kick stuff off of the stack. Let's see if I can actually. Okay, cool. What's going to happen is the stack pointer is one by one going to kick everything off of the stack and then return to where it was originally. And the reason is because after where you return, theoretically, we shouldn't have access to that stack frame anymore. So now that we see that this tealish part is underneath where our stack pointer is, this memory address, even though it's a memory address, is now invalid because we don't have access to it. Hence, it's basically going to be inaccessible and your program will segfault. So long story short, that's why even though you're trying to return pointers, not every memory address works, which is often what happens. I personally made this mistake like 2 weeks ago, literally, and I spent like 2 hours trying to debug it, and then I discovered I was returning something on the stack. But okay, so that's the quick overview, condensed version of memory in about 20 minutes, or less than 20 minutes, actually. Okay. That was really fast. Are there any questions up until this point? Okay. If there aren't, then we're going to move on to the questions for this part. I'm going to give approximately, so we're going to work through these parts. I'm going to give about 2 minutes to work through this. So that's like what, 5 rounds of Jeopardy music. So I'm going to, yeah, I'll just leave you guys to work on that. And if you have any questions, feel free to unmute yourself or put it in the chat. Will this work? Okay, so I know that might have not been enough time to work through it entirely, but we'll be walking through this part together, so hopefully that will help. Okay, so we're going to work through each of these, and I'll give a really brief explanation as to like why each one might be, and at the end, if there are any questions or like at the end of each part, if there's confusion, just let me know, and I'll go over it. Oh gee, my pen isn't working. Give me 1 second, sorry. Difficulty with electronics is our life now. Okay, cool. Okay, so for the first part, we're referring to the variable S1. So in this case, like, okay, so what it's actually viewing is, okay, so let's highlight it. So S1 is being declared here. So we know that from earlier, this is a string literal version, and we know that something that's special about it is it's one of the only ways that you can declare a string, or it's the only way that you can declare a string outside of like global variables that'll sit on the stack. So in this case, then we were like, okay, S1, that's going to be, or sorry, static. It's gonna be in static memory, right? That's actually not going to be the case, because notice what we're saying. We're referring to S1 itself and not what it's pointing to, because we haven't dereferenced it. We haven't tried to access it using array format at all. This just means that where is S1 itself sitting in memory? And because we know that it's within main, it's going to be a local variable. So the value, the S1 is actually going to be sitting on the stack itself. So I'm going to say not static. Hopefully it's clear why not. In a couple of parts down, we'll see why exactly not it's sitting, it's not in static memory, which actually I'll talk about right now. So like for this one, we see that it's S1 bracket 0. And what this is basically doing is it's equivalent to basically dereferencing S1 at the 0th location. If we were to do like S1, like, I don't know, 1, then it would have been equivalent to basically dereferencing S1 and then adding 4, because the reason is, or not 4, sorry, we're working with character pointers, not ints. So we're adding 1, so we're moving 1 to the next position. So these like are all equivalent, and because we're trying to access the memory now, and then we follow basically where the pointer is pointing to. The pointer is pointing to stack, or static, sorry. It's pointing to static. So essentially the memory here will be in static. I'm so sorry. I promise I know the difference between them. My mouth is just not cooperating. Okay, so for the second part, so part B, we're referring to the variable S2. So if we look at where S2 is in memory, so we're declaring it in the way that we described earlier, as basically having the compiler change as a string literal into an array. And so because we know that this is the same thing as earlier, basically, and we're referring to the variable itself, we know that this is going to be in stack memory. So now for part D, it's actually trying to index into that array. And so this is what's special about it, because even though it's a string literal, the compiler knows. It's like, okay, I'm trying to keep it mutatable, so I'm trying to keep it changeable. So now I'm going to basically turn this into a normal array declaration of a string. So then this ends up being in the stack and not the static. I can't spell. Stack, not static. So that's something incredibly important to keep in mind. Okay, so for part E, what we're referring to is now the character that's malloc. So pet peeve, I don't know why this is happening, but this is supposed to be a character pointer explicitly declared, not implicitly. Without it, basically if you try to compile, you're gonna get warnings, not errors, but it's just the compiler being like, hey, you're supposed to be, you know, casting this, but you didn't. So remember always to cast it, even if the example shown doesn't. So we know that because C is dynamically allocated, and this is trying to access the actual memory, we know that this, whatever it is going to be on the heap itself and not the stack. So for the last one, we're referring to the variable a. So the variable a is declared up here. Its int a is equal to 5, and because it's outside of all functions, we know that it's a global variable. And global variables, what's special about them is they're accessible basically from any function, and it's in read-only memory. So theoretically, you wouldn't want to be able to change it because you want to be able to rely on the value later on. So this would be in static memory. Happy static memory. Okay, so that was quick going through all of this. Just a quick recap. Are there any questions for this part? Okay, if there's not, we're gonna move on to the second part. If you think of anything later, just feel free to drop it in the chat.
Carolyn, I have a question.
Yeah.
Oh, sorry, my video is not on. Going back to your example of dereferencing on the stack, where you said we would get a seg fault. I think in lecture, Professor Garcia said that technically, we could dereference it and it might work sometimes, but it might not work.
Wait,
It's stack. Going back to the.
Oh, sorry, I keep cutting you off. Stupid.
Yeah, no worries. Yeah, going back to the stack, and you said that we couldn't dereference array. Sorry. Yeah, so the top right corner, you said we couldn't dereference that. That would give us a seg fault.
This, right?
Yeah, that. But I think Professor Garcia said technically we could, and as long as that stack frame hasn't been overridden yet, like a new function hasn't been called, it would give us some value. But so is it possible to sometimes get a seg fault and sometimes we won't get a seg fault?
So okay, so there's kind of it's a gray area. So the reason is because most C compilers, I don't know of one nowadays that doesn't give you those warnings. So what will happen is most modern C compilers, what will happen is if you try to run it, it'll basically seg fault you because it knows that you're not supposed to access things outside of a stack frame that you're currently at. So that's why the seg fault occurs. So then it's okay, it's making sure that you're aware of it, because what will happen oftentimes is this is something that's really, really dumb, but in lab 2, I believe it was, we were working with arrays, and as you saw, it seg faulted because it was an infinite loop. But if you tried it out in GCC, or online C compilers are pretty bad, don't take what they say as the grain of truth. But if you tried it with GCC, which is the official C compiler that 61C supports, what will happen is basically you'll notice that for a certain amount of space after the particular array, even after after it's ended technically, what will happen is you'll still be able to read and possibly even read from or write to the array. And that's something that's a little finicky, because it's well, why doesn't it know that it's the end? It's just because the array itself doesn't actually carry a length. So then it's okay, it won't seg fault until it reaches something that can be accessed. So it's sort of similar for this. Theoretically, if you read past it, the stacked frame, it's fine. It would be fine. And if like Garcia said, and as you said, if there hasn't been another function that was called and that would overwrite that part of the stack, theoretically your value is still there. What's just going to happen is in practice, if you try doing that, most times it'll end up giving you a seg fault just because it's really unsupported activity and you shouldn't be able to do that.
Okay, thank you.
Yeah, hopefully that clarification made sense. Sorry if that was a little confusing. Seg faults are special in the sense that it kind of depends on what compiler you use. Sometimes it will give you, sometimes it won't. GCC is what's being used by 61C and every upper div that requires C. So that's kind of our holy grail of truth of what will happen. Okay, so we're gonna move on to the second part. We're gonna go through this part a little bit quicker. So I will give you guys about a minute to work on this part. Essentially what's going on is the value that's presented foo, ampersand foo 5, ampersand 5, and ampersand X, basically rank them from the value that they hold from lowest in the memory stack to the highest in memory stack. So lowest being 1 and highest being 5. So I'll give you guys about a minute or 4 Jeopardy rounds to work on that. Okay, so we're going to go over it now. I know that definitely wasn't enough time, and I'm really sorry about that, but I really want to get to the next part, at least partially. So just going through some of this, I'll walk through the thought process, and if you have any questions as to why something is, remember, like, always feel free to unmute yourself. Okay, so how we're going to approach this is looking at each of these variables and what they're referring to. So if we look at the very first variable, okay, so foo itself, remember, we know that foo is declared here, and we also know that we're not referring to the memory of foo at this point. So what's special about this is when we look at foo itself, we're looking at the memory address, not like, or the value that it's representing, not necessarily like where it is on the stack. So this is like very different from the previous one. So we know that foo itself, if we try to do like print format foo, what's going to happen is we're going to print out a memory address. And the memory address it's going to print out is wherever this pointer is. So the reason is because whenever you have malloc, it's going to return a memory address. So in this case, foo is pointing to somewhere on the, foo is pointing to somewhere on the heap. So that means that whatever the value that foo stores, it's a heap address. So now we look at ampersand foo. So ampersand foo is referring to, now where is the variable foo itself stored? So instead of what's foo holding, it's looking at where it is currently. So as we know, foo, because it's within a main function, it's still a function. So we know that this is going to be stack memory. It's going to be sitting in the stack somewhere. So albeit it's going to be very early on in the stack, so it's still going to be in the stack. So this, keep in mind, it's early because it was the very, very first thing that was called here. So it's very early on stack. So then going through, okay, what's 5? So if we scroll a little up, 5 itself is just a global variable. And that being said, 5, what it's storing is the actual value 5. So that's a little funky. So like we're like, okay, that's not a memory address. That's fine. It just stores 5. We'll talk about that later on. And then looking at ampersand 5, because we know that it's global variable, it's going to be in static or data memory. So same thing. So this is going to be in static / data memory because it's declared outside of all functions, not just main. So that being said, now the very last thing that we're looking at is ampersand X. And if you're like, oh, ampersand X never got declared anywhere, that's really valid. And the reason that exists is because it's a memory, it's an argument to bar right here. So this variable. And because we know that it's an argument that was taken in at this point, so we call bar here, X is going to be set equal to 10 at some point, so it's considered an argument. We know that arguments are on the stack because it's part of the stack frame that was just opened. So we know that the address of X is going to be on the stack. And we know it's going to be a little later. It's later than the first one that's on the stack because we also know that it comes afterwards technically. So it's coming 2 after. So now we have to order them. So with 1 being the lowest, we know that static memory is technically the lowest, but we actually have something else that we need to consider. Because 5 is storing 5, if we have just a hex of 5, so 0, 0, 0, 0, 0, 0, 0, 5. This is essentially what we're talking about. And 5 is basically 5 bytes up from the very, very bottom of memory. So we know that that's actually going to be sitting somewhere, like the value 5 is value-wise, it's going to be very, very low if we consider it as a memory address. It's not in code, and it's most definitely like not in code, but because we're talking about the value, it's extremely low technically on the memory spectrum, which is why this ends up being the very lowest one. The next thing that we're looking at is going to be the static memory because we don't have anything that's referring to code memory. So, or actually, okay, I'm going to clarify something a little bit later on, but we'll just go through the rest of this. So static memory and stuff is ampersand 5, so we know that it's going to be second. So the next thing that's going to happen is, okay, so now we have heap memory. That's the next highest or next lowest on the spectrum. So we know that the heap is foo, so that's going to be 3. Now the last 2 things that we have to contend with are ampersand foo and ampersand X. And so the first instinct that we might be like, oh yeah, this is going to be 4 and this is going to be 5. That's actually not going to be the case, because something that we have to remember is that the stack grows downwards, which means that earlier variables sit higher in memory than the later ones. And that's because as stack frames open, they go downward, and as stacks close, they go back upward. So the stack itself grows downward with regards to being more and more recent. So in this case, foo is actually going to be the last one because it's highest in memory, and Ampersand X is going to be lower in memory because it's the most recent one that we're referring to. Okay, that was quick. Are there any questions for this part? If everyone feels kind of okay about it, we're going to move on to the actually the linked list part. I'm going to do probably like one subpart of this, and then I'm going to talk really quickly about floating point just at the very end. This one is just a one-liner. I'm just going to give it to you guys so that way we can move on to the more important part. So this line is going to be, I can't spell, it's going to be struct, oh my goodness, struct node pointer. The reason that it's not actually going to use the typedef SLL node, unlike later on, like for example, if we're trying to malloc space, we'd be like, oh yeah, SLL node star node pointer. I don't need the parentheses, I just realized. And then it's equal to like SLL star node star. Yada, yada, yada inside here. The reason that it's not like that is because basically when you typedef, anything inside that's referring to the struct itself needs to be declared in struct and then whatever initial name that you called it. Essentially what typedefing does is it gives the entire struct a nickname, so that way later you don't have to be like struct node every single time. So it gives it a particular name that you specify. But because that part hasn't been defined yet, because we're still within here and we haven't reached the end of the typedef part, then it's actually not going to be declared yet. So that's why we have to say struct node inside. Okay, so knowing that, we're gonna work on 3.2. Actually, should we work on 3.2 or 3.3? I'll give you guys about 2.5 minutes to work on 3.2. If you finish that early, then you can move on to 3.3. Okay. And if there are any clarification questions, remember you can always ask. Okay, so that hopefully was enough time to look through at least 3.2. If you didn't get to 3.3, that's totally okay. I'll release this, I'll send out the solutions afterwards, and if you guys have any questions, always feel free to follow up. Okay, so going to the first one, we're gonna convert the SSL node linked list to an array, and we want it to be an array of ints, not an array of nodes. So that's something important to keep in mind. Okay, so the very first thing that we want to do is, okay, we notice that we want to return the array itself, which is declared and initialized here, which means that we don't want it to be on the stack. So that means we have to malloc it. The solutions are going to have the non-casting of the pointer. Always cast it for good practice. In real life, sometimes like there are situations in which you want to keep the void pointer, as you'll see later on and in later classes as well. But for our purposes, all intents and purposes, keep it as casted. So we're going to malloc the space. So we want to malloc enough space essentially for everything. So we want to have the size times size of an int. And we don't want it to be node because we're not doing a node list. And one thing that's important is this is the case with string manipulations and nodes and things like that, or linked lists. You always want to pass in the size because there's no implicit declaration of like, oh, what's the length of a linked list here, unless you write obviously the function elsewhere. Okay, so we're going to go through while SSL. So while SSL is true basically and not equal to null, so this is essentially the same as being not equal to null. We want to set the array at index I equal to something. And so the something that we want to set it to is SSL pointing to the value. Now this is exactly the same as basically dereferencing the SSL pointer. SSL pointer, and then using the dot notations as we see in Java and Python, and as well as usually other languages, and we're going to call it value from it. You want to only choose one of the two to use, usually, because what I've seen happen is you use SSL and then you try to like do this. And while that may work, for example, if like, I don't know, dereferencing SSL creates another pointer, if it's like a double pointer initially, usually this is pretty much not valid. And so you usually want to stick with one of the two. That being said, now let's move on. So the next thing that we want to do is after we set the value, now we want to increment SSL. So by using SSL arrow pointer to next, we know that SSL next is going to be another pointer given right here. We know that it's a pointer. So we know that that fulfills our conditions. And so the next thing that we want to do is we want to make sure to increment I because we want to keep going basically until the end. And by the end, then we return the array itself. Okay, so that was pretty quick. Are there any questions with this? Okay, so I'm actually going to skip 3.3 for now. I'll come back to it at the very end if we have time. But just a really quick thing with regards to C and memory and pointers and whatnot, because I know that it's like kind of sometimes hard to like allocate memory using pointers or like figure out like, oh, what type should I use? So oftentimes what will happen is you end up defaulting to malloc for everything, and then you end up forgetting to free certain things. So just a quick like rule of thumb, essentially if you want to return something, either pass it in as a pointer. So when you pass things in as pointers, you're totally welcome to like pass in like Ampersand int. Like that's passing in a pointer and that's valid because it's coming from the outside function, which means that at least in the outside function, you'll have access to this memory. So you can either pass in a pointer or you can return something that's been malloc inside. So those are both things that are valid. And if you malloc something inside a function, you don't necessarily have to free it right away because otherwise you won't have access to that. So as long as you return everything that you're mallocing, you'll at least have some reference to it so it won't cause a memory leak. Something that helps me personally for like coding with C is like literally keeping track of where every pointer started and where it's last used. So by the time it's last used, I know like what's held inside of it and what needs to be freed. Because double freeing is totally a thing as well. Okay, so we're gonna move on to the very, very last part, which is the floating point intro. This is probably gonna be nice, quick and sweet. If you guys want like a really in-depth version of pointers, Steven uploaded all the discussions from this week, including Thursday's loss discussion and yesterday's discussion as well, which was the most in-depth normal length discussion out of all of them. So if you're curious about that or need review, those are two resources that I really recommend checking out. They're in the normal playlist for discussion 3 anyways. Okay, so going through, I'll just like blaze through the general setup. So floating point of what we're going to be using, it's called single point precision. And what this means is that we have 32 bits to work with. So oftentimes you'll see single precision floats. So what this is referring to is just 32 bits. Something else that you might see are like double precision. And that's basically just referring to using 64 bits. I don't believe we'll actually explicitly ask you to like manipulate anything using 64 bits in terms of floating point or calculating things, just because it's a little hard and it's a little tedious and it's the same thing. So I would say be familiar with how this looks. The standard type is 8 bits for the exponent and 23 bits for the significand. On exams, this might change because it's supposed to stretch your knowledge. So generally for practice, this is what you'll see, but be sure you understand what that implies when it comes to calculations, because you can't rely on exponent and significand both being 8 and 23 constantly. Something that's super important to keep in mind is that there are 2 ways in order to calculate the values for normalized and denormalized floats. So the other 2 types of values is like the infinity and the nan, which we'll discuss in like half a minute. So for those 2 don't actually have values that can be calculated because not a number is not a number, so it doesn't have a value. And then infinity is just positive or negative infinity, so we don't have to calculate anything. So that being said, something important to keep in mind is that these 2 are basically the same. They essentially use the same form of calculation with one very special topic. Okay, something I'm going to correct on this worksheet right now is because it's not in sync with the current discussion worksheets as well as the current lectures. This is, I think, the format from like several semesters ago, I believe. I want you guys all to correct this, and I want this to never ever be a point of confusion because it's oftentimes a point of confusion. So the bias in this class is always, for this semester, is always going to be negative. So bias is always going to be less than 0. For when we're talking about this, when we're talking about standard bias, what we're referring to is negative 2 to the n minus 1 minus 1. This is standard bias. Standard bias. This also means that as long as we don't specify a bias, this is what you can assume that we default to. So as you can see, then in this case, in order for this to actually work, we need it to be exponent plus bias. And please change this because, like, oh my goodness, if on an exam, like, because we're going to be using the plus format, if you accidentally subtract it, it's not going to be nice. So yeah, please remember this. I'll yell at whoever made the worksheets, I promise. So in this case, the difference between normalized and denormalized floats is that denormalized we have a +1. So this is super important because we know that for 8-bit numbers, so in this case, the 8-bit exponent, we know that the bias is going to be negative 127. So for both of these. So that means that for normalized floats, it's going to be exponent minus 127. And for normalized floats, for normalized floats, it's exponent minus 127. For denormalized floats, it's actually just going to be 126. And 126, it shall always be for denorms. The reason is because if we look at this chart, denorms have an exponent of 0. And that's always going to be the case. If you notice that the first half of the number, or like the first bits, cutting off the very first, like the most significant bit, the next 8 bits, if they're all zeros, then it's going to be on denorm. So we know that it's going to be 0 plus bias, which is negative 127, plus 1, which is negative 126. That being said, okay, denorms can have anything in the significand, and otherwise, other from that, the calculation is basically the same. The one other thing you have to keep in mind is that for normalized values, your significand is going to be these bits. But when you're calculating the values, you always have to do a +1 at the beginning. And the reason for that is because the range that we're trying to represent for normalized floats is basically above a certain amount that takes the 1 in order to actually function. So keep this in mind. When you're calculating it, if you're not getting the value that you expect, it possibly is because of the +1 at the beginning. The discussions will have more details as to like how this affects calculation, so I really recommend you guys check it out. This is just like a really quick like crash course in everything. For denorms, the very big difference is that it's a 0, so you can just basically ignore the +1 part and just treat the significand as it is. That being said, also something important to keep in mind that for normalized floats, the exponents go from 1 through 254 instead of 255. And the reason is because we take 255 to basically represent 2 other values. So positive, negative, infinity, which is 1 value, and then nans for another one. The reason that nans are non-zero for the significand is not because like, oh yeah, they're totally different values. It's because there are different types of nans. And in industry, in practical usages, nans are used for debugging oftentimes. So you want to be able to basically have different forms of it. Okay, so I will say, because it's technically 12, so feel free to head out if you need to. I'm gonna just like spend another like 2 minutes talking about floats real quick. A quick, like if you want to convert easily between floats, the couple of, especially decimal to float, because it's a little hard sometimes, something that I would basically I recommend is looking at the very first like truncate the decimal part and look at the very first part. And then take a look at that and be like, okay, how would I represent that in actual like binary? So like in this case, 10, the closest power of 2 is 4. No, 8. Yes. I'm dumb sometimes. Okay, so the closest power is 8, so it's 2 to the third, which means that you're going to be able to have some sort of like something like this. So we know that 2 to the 8 is going to be here. If this is 2 to the 0, 1, 2, 3. And then we know that it's going to be another 2 here. So we know that it's going to be some form of representation of this. However, something that we also know is that because there's only, it's like for the normalized status, it's only 1 point and then significand. It's going to basically only take this as the 1 here. So the rest of this is technically supposed to be in the significand. So that also means that we know that this is going to be multiplied by, because this is 3 positions. So like if we do it here, it's going to be 1, 2, and then 3 in order to get what value we want. So we're going to multiply it by 2 to the third, which is coincidentally this the largest possible power of 2 that fits inside our current value. So that's a trick that I like to use to figure out what the multiplicative value is. That being said, the 3 is actually equal to exponent minus 127 here, or exponent plus bias, however you want to think of it. So remember that the exponent itself is not actually 3. So something about that, then we have our last tail end to figure out. So the tail end, essentially, okay, so if this is our binary like point, we have like several spaces like ... after. So what each of these is referring to is like, because going to the left, it's 2 to the 0, 2 to the first, 2 to the second, etc. Then likewise, it's going to be 2 to the -1, 2 to the -2, to the -3, -4, -5, ... So what that represents is 0.5, 0.25, 0.125, and then etc. So it's basically the same thing. All it is 1 over 2 to the whatever absolute value it is. So looking at that, we have, okay, 625. How can we represent that? So the largest one that we can fit in is 0.5. So we have 1 here. Then we can't fit in 0.25, so that's a 0. Then we can do 0.125, which is actually coincidentally what's left. So we have 1, 0, 1, and then everything else is a 0 after that. So now we take a look at all of this stuff and it's like, okay, well, this is going to be what's in our significand, right? Right after the binary point? That's actually not what's going to be. The reason is because we have the multiplicative value right here, which means that actually in order to get, because this is what we get after we multiply by 2 to the third, it means that in order to get the original significand value, we have to basically shift everything right by however many, whatever value this is. So in this case, we have to shift it. Basically, we have to 1, 2, I can't do 1, and then 2, and then 3. That means we have a 0 here, 0 here, and 0 here in order to get that value. Coincidentally, that's also exactly how many spaces we shift for this. So these 3 zeros are actually not going to be zeros. They're not necessarily zeros. They're essentially what needs to get filled by the other green portion. So in the final solution, what would end up happening is we would have 1 point, and the significand is going to be 0, 1, 0, 1, 0, 1, and then 0, 0, 0, ... 0. So in total, this is going to take up 23 bits. And the way that it's split up is this stuff is the stuff that corresponds to the 10. This is the stuff that corresponds to the decimal part. And then we're multiplying it by 2 to the third, which is the multiplicative value with exponent equals 130. Because it's 130 minus 127 is equal to 3. And times our sign value. In this case, because it's a positive, we want -1 to the 0. So our sign bit is 0. So eventually you'll want to convert this into hex. So actually I'm going to talk about that really quickly right now because it's also a sore point sometimes. So if we convert this to like exclusively binary, we'll have, okay, 0 as the sign bit. Then we want 130 as the exponent bit, which I am going to do on the spot and hopefully I don't get wrong. We have 127 here and then none, 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 1, 1. Okay. So that's 1, 2, and then 127, I believe. So that being said, this is the exponent portion. It should be 8 bits, and then after that we have 0, 1, 0, 1, 0, 1, 0, 0. The reason is because 1 is an implicit one because it's a normalized value, so we don't have to include it. So now we want to divide it up to calculate the hex value. And one thing that you want to be careful of is not writing 0 hex, oh, it's 0, and then, oh, cool, I'm splitting it up like that. That's actually not going to be the case because you have to remember that this is still just a regular binary value, and if you try to represent it with hex, it'll still be calculated in terms of every 4. So in this case, we want to split it up by officially 4, so it's going to be split up here, here, I can't count, here, here, and then all zeros after that. So in this case, it's going to be 0 hex. Let me know if I get something wrong. So 4, 1, 8. This is 10, which is supposed to be A, and then A, and then 0, 0, 0, 0. That should be right. So our final value in hex, which you'll be usually asked to convert it to, this is how we represent it. So okay, that was a lot of stuff. We're also 7 minutes over time. Are there any questions as to the floating point or earlier the C part? And I'll spend the next 3 minutes or 2 minutes actually answering any residual questions, either about this or about anything related to 61C overall. If there are any questions, then yeah, also feel free to go. Our solution, so solutions, you mean for, so solutions for this worksheet, I'll be sending out actually right after this. Actually, the thing is, I'm going to be sending it out at the same time, and I'm going to be basically uploading this to online somewhere, so the recording, and so I'll send basically everything out together. So it should be sent out within the hour. If it hasn't, someone like ding me for it, because I'm going to be meal prepping after this, so I might it might slip my mind, but it'll probably take around half an hour to convert and upload. So that's I'll also upload the solutions or send out the solutions with that. Cool. If there's nothing else, thank you guys for coming. Hopefully this was helpful. I know this says quest review, but it's post quest. I'm kind of annoyed about that. Wish it happened before the quest. But hopefully this is a good review for the midterm, and it cleared up some concepts. Okay, I'll stop the recording.